Hello, welcome everyone. I am Simran. I am doing my PhD, or here what you call in Oxford a DPhil in engineering. Um, we will be looking into insights of sciences and then the importance of math and physics. How do we actually use or utilize the basic concepts of mathematics and physics in order to study higher education in higher education, for example, in engineering, or if we end up doing particle physics, that's a sub branch of physics as well, nuclear sciences, and so on. Um, what I do basically in my PhD, I'll just give you a basic outline, and then we jump into one or looking into a couple of concepts, what you might come across if you end up taking sciences in general or engineering in general or any other scientific field for that matter. So I hope you all have seen airplane engine, how they do look like, right? Um, they have blades which rotate at a very high speed when we talk about during operation. And just for example, this is quite common problem when a foreign debris, in any form, such as say a flying bird or volcanic ash, when flying above the volcano, they hit the blade and they do some sort of a serious damage to the blade. And it's a computer simulation. How does it actually look like? So if I just play this again, so if you see it's kind of flutters around and it vibrates at a very high velocity. Here you can see it with your naked eye that it is the color is changing. What this color basically tells us, the red is the most intense deformation that has actually happened. And when we talk about blue, it's a little, um, it's a minor deformation in the blade. When we talk about yellow, it's significantly more, and red is just the extreme case. So what I do, I study these cases um, in terms of how much damage is done to the material and how we can actually solve this problem. Because if this vibration just continues for a longer period of time, we end up breaking the blade, and and the consequences would be faced by the passengers who are sitting actually inside. So this is the same kind of problem which you must have watched the Hollywood movie Sully. If you have not, then you should. That actually gives you an insight if in case airplane engines are not working, they're no longer operational in the midair, then how a pilot can actually save the life of the passengers. Okay, whenever we talk about something which is happening in the real time, especially in sciences, we can't every single time run an experiment because running an experiment, they are costly. And we run the experiment initially, but we try to bring that experiment with the outcomes of that experiment into the computer so that we can simulate things, we can represent our experiments into the computer model. And when these things are happening, that can actually save time, that can actually save a lot of money as well, and lots of resources and lots of space that comes into resources itself. So what is a mathematical model that we talk about? When we say mathematical model, it involves hell lot of equations, mathematical equations, which are motivated by physics. So when we say we have a real-time situation, say for example, an airplane is flying, but then if you were to given an equation, say in the early 1900s, when actually the first plane which was actually being manufactured, um, they manufactured the airplane, they then tested it, but then straight on after manufacturing, it was not simply being available for public, right? Because there could be devastated consequences that the passengers might have faced. So what they tried to do initially, in those days there were no computers, so they just keep on iterating with say statues or until the airplane is fit for flying. But nowadays, what we do basically, when we have made anything, say for example an airplane, then we try to simulate how how things would work in the computer model and vice versa. So the first the computer model, then the actual presentation of the physical representation of that model in the physical sense. So how things work in the real world when we have a real-time situation, we we convert that into mathematical model, we get some results, and we kind of validate those results with the experimental outcome that we have got. So it's kind of overlapping things, and we see how up to what extent these things are actually being overlapped. For that matter, what we sorry, yeah, here's a brief video for you how mathematical models. It's a very brief video that talks about how mathematical models are actually being made, and what are the parameters do we actually look for in a mathematical model. So I'm just going to play this video and then I'll explain you things in a lot more detail. Now, here, what this person is talking about, there are multiple, he has actually talked about multiple stages of mathematical model. So in the first one, like I explained very briefly earlier, that we have a physical situation that we actually want to replicate because running experiments all the time, they are expensive. So we try to replicate with a bunch of governing equations that are responsible for running the mathematical model. Once the mathematical model is ready, we are good to go. Then we run those things. But in the real world scenario, not everything we can actually represent in the model. So for example, density of air. When an airplane is flying, as soon as it takes off and when it is cruising, the density of air, it changes. It changes with height. How do we put those things in the mathematical model? If we have that equation that actually can make the density changing with time, it, we are good. But then as long as we do not have that, then we need to assume that the density would remain constant. So likewise, we need to assume a few things because we are trying to replicate the real world scenario into the model. Then once the model is ready, it runs, the data is collected, then we make comparisons. We try to validate our model because we want model to be as good as the physical world scenario. And then we do a bunch of analysis, we do data analysis basically, and then wherever we see that there is a jump or there is something which is not actually appropriate, then we try to refine the model. We try to put more and more parameters in. I'll explain you in details what parameters I'm talking about, but then those parameters which are currently present in the mathematical equation. So for example, we are calculating force acting on an object. So when we say calculating force on an object, then we need what? We need mass and we need acceleration for a moving object, right? So that mass and acceleration, these two things are actually the physical parameters that we actually want. So we try to refine those parameters in order to refine the model, in order to make the model better, in other words. Now, now we have that scenario, we have a problem situation. and we will formalize something. And then once the formulation or the bunch of equations are ready, then we analyze that problem. Then once the analysis is done, we obtain the data in a graphical format or any format that you like. We compare them, and then we refine again. And this loop just simply keeps on continuing until we get the utmost precision that we want. Now, we'll take a break from this presentation. I would like to show you something while drawing so that you can actually understand a little better. Let's say we have a football or any ball for that matter, right? We have that air that is streaming down. So let me represent that air with a v infinity. So it's called the free stream velocity. Now, that air is coming across this object that is the ball that we have. Ideally, what we want is this air surpasses that ball and separates here. Similarly, on the downward direction, it should go like this. Because as per Newton's law, we want um, that that flow to be separated on the same side, on the opposite side where it is kind of hitting the ball. Why do we actually want that? That is because if there is a force which is acting F1 here, force acting F2 here, ideally it should be F1 equals to F2 so that there is no net force. But in real world, what happens if we have a ball similar, pardon my drawing, but um, if you visualize, it just gets separate here itself. What is happening in this case? In this case, we have F1 is greater than F2. So when we do theoretically, when we analyze something theoretically, then we would consider the scenario, that is scenario number 1. But in the real world, in practical scenario, we'll get situation something which is situation 2. So how do we actually deal in with? In this case, when you are making mathematical models, so certainly in this situation, you have to kind of assume a few bits. Here, assumptions will take place because you can't achieve situation number 1. It's in an ideal scenario, you would like to achieve this, and up to some extent, it can be achievable, but when we get the theoretical results, getting theoretical results are sometimes difficult. So in that case, we assume things. Now, if we think about the operation of an airplane, if I just simply draw a miniature model of an airplane, yeah, yeah. So if you look at this cross section, these are the wings. This is fuselage. When we do practical examples, in that case, when the airplane, for example, is ready to fly, right, or to begin into operation, the manufacturing industry, they said we are ready to sell this airplane. How do they test this? They test each and every component of this airplane. It has a rotor, it has wings, it has fuselage, it has aileron, multiple other components as well. They test those components separately under the wind tunnel. That wind tunnel tell them how much amount of drag that they might come across, and how much amount of thrust that it can actually generate. Now, how are they going to test this? It's absolutely impossible to take the entire airplane inside the wind tunnel, right? As far as I remember, we do not have such facility in the world existing at the moment. So when they pick up each and every component separately inside the wind tunnel, they represent that in the form of an airfoil. Just like the human structure, we humans, we are made up of bones, multiple bones. So bone in our case is the fundamental, if I can say, if I can use the word component that we humans are made up of, then airfoil, that's a fundamental sub component that an airplane is actually built upon. So whenever we have to test how much drag it is coming across, then we just test it on an airfoil, or any experiment for that matter, we do it on airfoil. Now, if I pick this airfoil and would like to see how actually an airplane fly, a new model of an airplane fly, so I can put this airfoil in an wind tunnel. Oops, let me change the pen again. Let's suppose this is the free stream velocity that we are coming across. Let me just focus on one layer of air that hits at this point. This is the point where this is an ideal point where air, the layer of air that comes hits this part, let's say this is point A, and it just simply gets stagnant here itself. It does not move anywhere. That point, we say it's the stagnation zone. And at this point, because it is not going anywhere, so the pressure is maximum. That we call in technical terms as stagnation pressure. Now, the other bits, when we call other bits of air, they travel through, let me change this one to green, yeah. The other layers, they travel through and they just simply get separate, say at point B. We have another layer on top of it. This comes here. Just get separate here. Now, what I said earlier, that we ideally want air to get separate at this point, at the tail. This is the trailing edge, sorry, the leading edge. This is the trailing edge of an airfoil in order to reduce drag. But in this case, the airfoil is coming across a lots of drag. What it is basically doing, we need to understand how we can reduce the drag. Then how do we have seen this in an experiment, but then we want to replicate in the model. How do we do that? We will pick up a very tiny portion of it. We'll see what is happening from here till here. What is happening here? So in order to, because so for example, it has a curve, right? This airfoil has a curve. In order to simplify things when we model, so we would consider something that is quite flat. Let's say it is an infinitely long plate. It's an infinitely long plate and with a very minimum thickness. Now, we again have an V stream flowing through. And if we focus on the first layer, it just stops here and then separates. The other layer, layer number 2, comes at the top, travels a little further up ahead, and separates. Layer number 3 simply comes across and then separates somewhere here. What is happening here? If you just simply zoom in that region between this and this, let's just zoom in. What is happening here? When the layer of air it's coming across, it gets separate after a little while because of the friction effects that are happening in between the first layer and the plate or the surface at the interface. So it gets separate because of the friction effects. It just slows down. So for example, if the velocity of this air layer was V1 at this stage it's V3. V2 is somewhere in between. So the velocity is kind of slowing down. When it is slowing down due to the friction effect, the layer number 2 that is flowing at the top of it, it can actually travel a little more because it is not in contact with the interface as much as the first layer. So it can travel a little further up ahead. Similarly, with the third layer, it can travel a little further up ahead. The the expression that we can actually deal with in order to calculate the drag comes down as d is equals to 1 over 2 rho v a c d. Here, this rho is the density of air, v is the velocity, a is the area of cross section, and cd is the coefficient of drag. Let's suppose if we are replicating this scenario in the real world equation to our simulation, that being our assumption could be rho is constant, although it is not. It may not. It depends where this principle is actually being applied. Is the aerodynamic scenario we are talking about in the rockets when they are at the time when they are leaving the Earth orbit, or we are talking about cars in the automobile industry? We can consider this rho as constant, pretty much constant. But with height, we know the density changes. So, but for the assumption's sake, we just say that it is constant a little bit. V, it is varying. So V is a function of time in this case. Area we know area can be constant, and that CD, that coefficient of drag, that depends on the area of cross section as well. So we'll say this as dynamic. What I'm trying to tell you here is different. When we talk about different scenarios of the real world problem, when we try to simulate them, it depends on where we actually want to utilize that in terms of their application. So that can be different according to the purpose. So when we understand that the velocity is going to be different, then we move back to the airfoil. What are the things that we can actually apply to that airfoil so that our flow separation can be delayed? So we want ideally that flow starts from here, travels all the way, and become as delayed as possible. Ideally, we want at this point, but let's see how we can do that. There are multiple set of things that we can actually apply. Let me just draw that airfoil again. Now, so we have V infinity as the free stream velocity coming up to the airfoil. First thing, this is the initial case that I drew earlier that it is separating here. So this is, let me write this up, initial. And we want the flow to be traveling a little further up ahead. In that case, we will try to use some dynamic structures which are called as, I'll write the name here instead, vortex generators. What they do basically, if you understand the chronology, we went there to understand where the flow is actually getting separated. We know the distance. The first layer separates here, x1. Second layer separates here, x2. We know these distances. And similarly, we know distances here where it gets separated. So we put these generators at the same location where the flow was just about to get separate from the body. So what do? We make use of vortex generator. What they do basically, if we have, sorry, if we have an infinitely long plate and the flow was about to get separate here, we will make use of these generator, which they look like this. And as soon as air comes here, and at that location where it was just about to get separate, it just turns around, rolls in, and produce some eddies. And the delay, which was supposed to be at location A, would now be at location B. So we have delayed the flow using this vortex generator. They produce eddy currents. What eddies do? They kind of create turbulence in that region if they do not find the surface is smooth enough. This infinitely long plate, there was an assumption that this it is frictionless. But now, as soon as we introduce some kind of roughness onto the surface, then it would produce some eddies. Now, for example, if the following layer on top of it, now it would just mix with the eddies that were actually generated by the previous layer, and the flow will travel a little further up ahead and then get separate. So we are delaying things. Now, as long as we have seen these, what do you expect? Would you like to just keep on using the wind tunnel in order to understand where the flow is getting separated? That's one of the ways. But then in complex scenarios, on the complex geometries, here it was just an airfoil. But then when we talk about complex geometries, such as the engine blade, or such as the entire combustion engine itself, then you can't just simply use the fuel or use the electricity in order to run that engine and the wind tunnel in order to find that spot. So what do? You just run it once and then you do the computer simulation and then try to find that spot. How do you do that? Because you know you have created your computer model, try to be as precise as possible, and then you have got that spot tentatively that this is going to be the spot. And then you use the different sizes of vortex generator, right? You used different sizes of vortex generator in order to see how much this flow can be delayed. So it's kind of getting some information from the experiments and again putting it into the computer models in order to solve the problem. If that problem is solved, what you expected, it's fine. If you felt like there was a requirement, there was more requirement to be more precise, say you wanted to get this flow to be separated at this spot, changing the density, would that be an option? Go ahead. But if you feel like there was a room for more improvement, then you keep on running some more simulations and try to find that answer, because running simulations in computer is relatively easier than running very heavy experiments because we require manpower as well. So that was one aspect of finding a right spot. Now, if we jump into, yeah, there are multiple types of models that we come across that we can run in order to get our solution or and to get the simulation as precise as possible. So what we do, we have multiple models, and these models are actually uh, uh, defined as analytical and algorithmic model. Analytical model, they just use very basic equations, and they are not very dynamic. They can solve 1D or 2D problem, but they can't just simply go ahead and if you indulge them in with too many parameters. In that equation that I showed you as drag, 1 over 2 rho A V square CD. So that equation was a very a one dimension equation. But then if we talk about running complex simulations, that we need more and more equations. Maybe solving a problem or running a simulation with just one equation is never enough when we talk about when we talk about heavy engineering problems. So in those cases, we use bunch of equations, and analytical models, they actually fail over there because they use some sort of an approximations um, in order to run, but then we want more precision because, like I said, if something goes wrong, then we are talking about the passenger who might face the consequences. Then we jump into algorithmic model. In those cases, we have a bunch of numeric simulations that we run, and these algorithmic model. So you must have heard about MATLAB, C++, Java, those long scripts that people write. And over there, one equation is actually connected with another equation. And when you run in a sequence, when you run those equations in a sequence, then you just keep on getting that data. So for example, they can just simply draw in a code itself, they would draw um, the geometry that you would like, depending on the width, depending on the height. Then once the geometry is drawn, suddenly the next equation would actually run. Next equation would talk about what is the density of air that you're considering, what is the area of cross section, and how much would be the velocity of the air. Would that velocity change or not? If not, then how are you going to change that velocity with time? And how the stagnation pressure would look like, and what would be the area of cross section, like I've mentioned earlier, and then where that flow separation you are looking for. If you're looking to delay the flow separation, then how much would be the height of the vortex generator and width of the vortex generator, and what is going to be the intensity of the vortex generator that the eddies are being generated. And accordingly, you are just visualizing on your computer screen, you are basically visualizing how the flow is actually flowing across the airfoil. And similarly, if you use further more complex equations, then you can actually visualize how the flow is actually moving across the airplane. And when we talk about how the flow actually moves across the airplane, then in that case, we can actually talk about how much is the aerodynamic efficiency. What is the overall aerodynamic efficiency of an airplane? Airplane, it has got multiple parts over there. So if I just talk about, this is the a rough sketch. This is kind of a rough sketch of an airplane. And then, like I said, we have wing section here. Wings, they actually have flaps. Then we have yet another control surface, which is joined by another control surface here. This we basically call as rudder and aileron. Now, without these control surfaces, your airplane cannot fly because you need to do pitch up, pitch down, rudder, that is your moment, and aileron in order to rotate the airplane, in order to reach your destination. If you have these control surfaces, only then you can actually be able to fly an airplane. Now, in order to calculate the efficiency or to determine the efficiency of these control surfaces, you need to be very, very careful how good they are, how efficient they are mid-air. And these control surfaces uh, that they're combined with the airplane, you again test them in a similar way. So what basically we have seen in a brief period of time so far, that every component of an airplane is actually being used in an isolated manner in order to run the simulation on after the experiments, and in order to calculate the efficiency, how good they are, so that you are ensuring the safety of the passenger at the same time. And which is why when we talk about science in general, it is it is a it is such a huge field that you run experiments, you do experiments, you do all sorts of data analysis followed by the experiment. But then where are we actually going to use that data? That data is actually being utilized to conserve it into computer simulation, so that computer gives us the answer, so that the next person who arrives to do an experiment do not have to do the entire experiment, or not even a hint of an experiment, because repeating same experiments which will delay the progress. So, which is why, as a scientist, as scientists, we actually tend to generate data. We publish them in order for the community to actually go through that data and run the simulation, so that they can improve those simulations, so on and so forth, in order to make them available for the community for the better use. So this is the time where I end. I hope you have liked the lesson, and if there are any doubts, I'm happy to take doubts or any sort of questions or any comments, even if you have, then we can end the session on time.